is dropping towards 0. It never reaches 0. So what we do is we put a dotted line here like this, and then we just put an arrow like this. Oops, I don't mean to touch there. An arrow like that. And this is what we refer to as a horizontal Do you all know how to say that word? Asymptote. It's a weird word. A horizontal asymptote. These functions we've studied, none of these have this characteristic of a horizontal asymptote. I look at the horizontal asymptote as like a magnet, okay? Like a magnet, you know how a magnet can repel, like push something away or pull it towards? I look at a horizontal asymptote as like a magnet that pulls the graph towards it, right? What's happening is you're trying to draw the graph this way, but the magnet's like, nope, you're going to come down here and get closer and closer and closer to me, right? That is a characteristic of, well, a possible characteristic of rational functions. Not all rational functions have this, but a lot of them do, all right? Okay, let's see where else, because this is a little bit, you know, we're talking about people and their lives. You could do something like this for, you know, anything that's like a light bulb, right? What's the chance when you put a new light bulb in, right? What are the chances that it works in the beginning? Pretty good, right? What happens a year later? Well, it's probably still working, but, you know, it's going to taper off. Can you tell me that that light bulb won't come on in 150 years? You can't tell me that, right? It might come on, right? It might still work. So another example, our phones, right? Our phones, our batteries in our phones. What do those cell phone companies do with your battery? Yeah, like the chance that your battery is going to take a full charge and last a certain amount of time, right? What happens? In the first 2 years, pretty damn good, right? First time you plug it in, you're like, holy shit, I can go a week on this thing, right? And then like a year later, you're like charging every 7 hours, right? What happens? They make your battery do this, right? They manufacture the battery so that they don't last. They do it on purpose, right? Because they want you to get a new phone, right? So they make their batteries only do this, and then it drops down significantly. All right, is this okay? I'm just trying to show you a place in the real world where we need to model something, and the functions we have so far don't do it. All right, so you ready to see what a rational function is? Like, I'm going to define it for you. It's going to be very easy for me to define, but it's going to be not very nice once you understand what it is. Okay, so a rational function is a function that looks like this. Real simple, okay? It's a fraction, okay? It's a fraction, which is where the word rational comes from the word ratio meaning fraction. So it is a fraction. It's a function that is a fraction. And the numerator is a polynomial, which we just studied, right? We just studied polynomials. So you take a polynomial, you put it in the top, and on the bottom, you put a different polynomial. And now you've created what's called a rational function. So a rational function is the ratio of two functions that we just studied, right? Like the one we just graphed right there. If I take that function and put it up top, and then maybe take one of your homework problems or whatever and put it on the bottom, now I've created a rational function. All right? That's it. That's what it is. All right? The good news is that what we learned about synthetic division and how to factor and stuff is going to play right into this. The hard part is going to be we're going to have to analyze a lot of different things. All right? These are the hardest functions to graph, in my opinion. These are the worst ones, all right? Because there's so much involved. So that's the definition, and now we're going to start with our first example. And the first example we're going to look at is kind of the classic problem. And you've actually seen this function before. This is what's called the reciprocal function. Remember the toolbox functions, all those functions we needed to kind of know what they look like and all that? This is one of them. And at the time, you didn't know this was a rational function. But it is, because if you look at the top, that is a polynomial. It is. It's just the constant one function. Well, that's a line. That's a line, isn't it? If I just say draw the constant one function, that's a line. So it's a linear function on top. Linear functions are polynomials. And on the bottom, that's just what? X? That's another line, isn't it? Which is a polynomial. So do we have a polynomial divided by a polynomial? Yeah, it's just, this is like a super simple one, all right? Hey, what happened? Come back. Okay. So the question is, what does this look like, right? What does this look like? And especially because a lot of you are going into calculus, I know this. What we're about to do right now is very important that you understand the relationships of numbers, all right? So I want to try and graph this, but I want to do it using an old school method. And we're not going to use this like the rest of the way. This is just so you can see what this looks like this first time through. I'm going to graph this by making a good old-fashioned t-table. A t-table is where you actually like plug in different values and see if you can start plotting points and get an idea of what the shape of the graph is, all right? So let's start out, I don't know, I'm going to start out with 0. Can we plug 0 into this function? What happens if you try and plug in 0? 1 divided by 0. Can't divide by 0. So right away we already have a problem, don't we? It's undefined there. This function is undefined. It's undefined at 0. Okay. Let's try 1. What happens when you plug in 1? You get 1 over 1, which is just 1, right? Let me try doing this graph over here. When I plug in 1, I get 1, right? There's a point. That point lives on my graph. I plug in 1, I get 1 to come out. How about if I plug in 2? 2, I get a half, right? So at 2, I'm halfway up, right? You see what's going to happen? Plug in 3, I'm going to be at what? 1/3, 4, 1/4, 5, 1/5, 10, 1/10, 100, 1/100th. Do you see what's happening? Getting smaller and smaller and smaller. So as you go out to the right, this thing is going to drop down. Now, does it ever reach? No, because even if you went out to a billion, right? What's 1 divided by a billion? Tiny little number, isn't it? Positive number. So what we have on the right-hand side is a magnet, right? A horizontal asymptote. This is a I'm going to put HA instead of horizontal asymptote. That's a horizontal asymptote, and it comes like this. Any questions? Everyone understand? It's just it's dropping away. So the calculus perspective is this. If you take a number that's fixed on top, you see how that number on top is fixed? It's 1, right? It's not changing. What happens if you take a fixed number and divide it by numbers that get bigger? What happens to the ratio? If you have a fixed number and you divide it by a number that gets big, that ratio gets small, right? It gets small, it heads to 0. All right, let's do some negative numbers. How about -1? So at -1, what would I get? I get 1 over -1, which is -1, right? So at -1, I'm at -1 right here. Okay, what about at -2? 1 over -2, that's -1/2, right? So isn't that like a little further up? Like right here? Right, that's -1, so -1/2 is right there. Yeah, so this looks like it's doing the same thing this is doing, right? The further I go this way, it gets closer and closer to what? 0, right? But from the bottom instead of the top. So it looks like this, and hey, we still have that horizontal asymptote over here, don't we? So let me try and give you the calculus again perspective on this. If you take a fixed number, right, a fixed number like 1, and you divide it by a big negative number, you're going to get a small what? Negative number, right? This is a small negative numbers. They're getting smaller, but they're negative because the ratio of 1 divided by a negative number would be negative. We all right? That's almost the graph. There's something else we have to entertain, which we haven't talked about, and I'll do this in a different color. And that is, I know I can't plug in 0, right? I can't plug 0 in. But what happens when I plug in a number like, I don't know, right here? How about if I try and plug in 1/2 into this? So let's try and plug in a half. Plug in a half. 1 divided by a half. What's 1 divided by a half? 2, right? Because 1 divided by a fraction, you flip the fraction over. So this is 2. So that means I have, at 1/2, I go up 2. I'm right there, right? Now that's actually the same color. It's part of the graph, whatever, right? Okay, could I get a number closer to 0?
1/3.
I could do 1/3, and what would the answer be? 3. Could I do 1/4? 4. 1/5? 5. 1/6? 6. 1/10? 10. 1/100th? 100. I keep doing this forever, couldn't I? 1/1000? 1,000. So what's this graph doing? It's taking off, right? It's going, it's like launching off to infinity, basically. But it never, you can never actually have anything at 0. So what we put here is a vertical dotted line like this that goes up through here, and we call this a vertical asymptote. A vertical asymptote. Similarly, if I were to have come in on the other side, right, and put in like -1/2, -1/2 in here would have given me what? 1 over -1/2 would be -2, right? -1/3 would be -3. -1/4 would be -4. -1/5 would be -5. Got it? So it's doing the same thing this way. And that is the graph of the most basic rational function we could ever look at, 1 over x, all right? Yes?
And then when do we have a hole at x equals 0?
We don't have a hole, we have a vertical asymptote at x equals 0. A hole is something different, which I will talk about, all right? So let's kind of recap on this right now. Horizontal asymptotes, right? The horizontal asymptote we have is like a magnet that pulls the graph, but only at the edges. Okay, so you remember with the polynomials we just did, I gave you that table, and we have those different cases, right? This or that or that or that. We don't have that here. What we do have is that if we have a horizontal asymptote, it tells us what our end behavior is, but only the end behavior. It pulls our graph at the edges only, right? Then we have this thing called a vertical asymptote. And vertical asymptotes are not, I mean, I guess you could look at them as magnets. I look at them more as like barriers. So like if I'm trying to draw this graph, I have this dotted line that goes all the way through here. And it's like my graph sees the wall. It's like a wall, and the graph's like, shit, I got to keep going, but I can't hit the wall. I'm not allowed to cross through the wall. So what does it do? It dives down over here, right? And on this side, the graph's like kind of going towards that wall, and then it has to like turn up so it doesn't hit the wall, all right? So verticals are like vertical barriers that you can't cross, and horizontals are magnets that give you end behavior. With me? Okay, does this graph have any x-intercepts? Does it ever hit the x-axis, ever? Not this graph. Do you think it's possible to have a rational function that does? Maybe, maybe not, right? Let's look at our next example. You could do transformations, like shift this one up or down or something like that. I want us to look at this function right here. Yeah, x over x minus 3. Okay, and one more thing. All right, that might be a little hard to read. Let me see if I can change that a little bit. Might be a little bit easier to see there. Okay, what you see over there is a new example. I'm having the computer graph it for us. It's the function f of x equals x over x minus 3. Okay, is that a rational function? Yes. It's a polynomial divided by a polynomial, right? Now, it happens to be a linear function on top and a linear on the bottom, but it is still a polynomial over a polynomial. The question is, right, what does it look like? Well, we're going to cheat, okay? We're going to look at the graph right now. We're going to look at the computer. We're going to look at the graph. And we're going to see if we can't find some relationships between this function and what we're seeing there. So take a look over there, and let me first ask you on that picture, do you see any x-intercepts?
Yes.
Where? Where does that thing hit the x-axis? X equals what? 0. So I have an x-intercept, right, at x equals 0, right? Y'all agree? All right, do you see on that graph any vertical asymptotes? Do you see any like vertical barriers that seem to be forcing our function up and down? And can you tell at what x value it's happening? Looks like x equals what? 3. Let me show it to you. There's the barrier. Right, do y'all see that barrier right there? Now that dotted line is not part of the graph. It's just there to aid you in seeing it, right? So we have a vertical asymptote at x equals 3, right? That good? Questions? Oh. All right. How about a horizontal asymptote? Let me zoom this. I'm going to kind of zoom this way. Look at this graph. Can you tell what it looks like this thing is the magnet it's being pulled down towards? It's not the x-axis anymore, is it? Do y'all see that? If I keep going to the right, it's not the x-axis. It's something else. Can y'all tell? It looks like what? 1. Y equals 1, right? It looks like y equals 1. If you don't believe me, I'll show you what y equals 1 looks like. Where is it? Okay. Yeah, that's what I want. Do y'all see that? Do you see the red dotted? Doesn't it look like that red dotted line at the edges is like a magnet pulling it down? So I have a horizontal asymptote at y equals 1. Okay? Anyone have a question off the visual inspection of that and how we're identifying the x-intercept, vertical, and horizontal asymptotes? No? All right, so if you understand that, then I want you to now, let's look at our x-intercept, and let's go back and look at the original function and tell me where you might guess as to where that x-intercept came from in that picture, in this function. What is it? Go ahead. So if you plug 3 into this, you get 0 on the bottom, don't you? And 3 into this, isn't that the vertical? Right? Okay, but you're seeing a connection. That's all you need to see. Does everyone see that possibly this 3 is coming from setting that equal to 0? If you set the bottom equal to 0, what would you get? 3, right? I wonder if that's where this comes from. On all rational functions, wherever the bottom is 0 is where you have verticals. I wonder, right? What about this? Where do you think this comes from? Setting what to 0? The top. Just the top, right? If I asked you right now, set the top equal to 0, what would you tell me the answer is? 0. If I say set the bottom equal to 0, what would you tell me the answer is? 3, right? It looks like that's where they're coming from, right? And I'm here to tell you, yes, that's indeed exactly where they come from. You can always look at a function. Wherever the top is 0 is where you have x-intercepts. Wherever the bottom is 0 is where you have vertical asymptotes. I'll write this down later. I'm just trying to get you to see it right now. The hard part, the hard one of these is the horizontal. Y equals 1. Where in the hell does this come from, right? Where does that come from? And that, I will be honest with you, is harder to see. I have to explain it to you in detail, all right? So are you ready for me to explain it? Yes? Okay. To find the horizontal asymptote, we are going to look at the degree of the numerator and denominator. What is the degree of the numerator? What's the degree of the numerator? Numerator is the top, right? Denominator is the bottom. What's the degree of the numerator? 1. Okay. What's the degree of the denominator? 1. Okay? They're the same, aren't they? In the case that they are the same, okay, in the case that they are the same, and don't worry, I'm going to write all this down in a minute, all right? In the case that they are the same, to find the horizontal asymptote, what you will do if these are the same, is you're going to take the number in front here and the number in front here and take that and divide by that. So what would 1 divided by 1 be? 1, and that's where the horizontal asymptote comes from. But that's only if these powers are the same. What are the different cases? This power could be what? Bigger than that, right? Or this could be smaller than that, or they can be the same. So when it comes to horizontal asymptotes, there's actually going to be 3 different cases we have to look at, or that we could potentially see. All right, and we're going to get into it. Let me give you another one to look at, all right? Okay, take a look at that. And I need to write the function out real quick. Hold on. This is the function f of x equals x squared minus 4x minus 5 over x squared plus 3x. Okay, there's the graph over there. Take a look at that graph. Let's start with x-intercepts. Can you tell from that graph where we have x-intercepts? Let me see. Yeah, I'll zoom in a little bit more so you can see them. Y'all see them there? Our x-intercepts are at -1 and 5. How about vertical asymptotes, where we have vertical dotted lines? Do y'all see them? It's a little hard to see. Do that. Where do you think? X equals -3. Let's try that. X equals -3. And where else? X is 0. Looks like we have 2 of them, right? It's hard to see this one. Do y'all see that that's dotted? That's not very good. Let me fix it. I will do this. Let me make it red, and let me make it bigger. There we go. That way you can see it. Do y'all agree? -3 and 0 looks like where we have 2 vertical asymptotes. -3 and 0. And then how about horizontal asymptote? Can you tell? Kind of. Let me zoom out. This one's harder to see. What does that look like? It's flattening out towards. It's 1 again. It's 1. Look, the horizontals are hard to see sometimes on a graph, but it's 1. All right. And you know what I should have done here? Y equals 1. I should have put here x equals, just to be clear that these are x values. So it was It was x equals. I've already forgotten. It was x equals -1 and 5 for this. And for the verticals, it was x equals 0 and x equals -3, right? So I wonder, do these x-intercepts come from this? Yes, they come from setting this top to 0. What if I told you to set the top to 0? Wouldn't you factor that? Now I'm gonna just go right to the factoring. I'm not gonna show the step. And then I'm going to factor the bottom. They both have an x. I can pull an x out, and I get x plus 3. Do you see all I've done is factored? So if I factor this, and it becomes this, if I set that to 0 and that to 0, what are the 2 answers I get? 5 and negative 1, and that's where my x-intercepts are, right? If I set that to 0 and that to 0, I get 0 and negative 3, and that's where my two vertical asymptotes are. And then the horizontal asymptote, let's do that thing. Compare the degree of the numerator and denominator. What's the degree of the numerator? 2. What's the degree of the denominator? 2. They're the same. So I take the number here and the number here. What's 1 divided by 1? 1. Okay? All right. All of this is just to get you to get an idea of what they look like, what the connections are between the x-intercepts, vertical asymptotes, and horizontal asymptotes. Now what I'm going to do is I'm going to give you, what do I want to do? Let me give you one more example before I give you the steps. I need to give you one more. And this one I haven't graphed it for you, so I'll type it in once I put it up here. So how about this one? Let's do a new one. F of x equals, let's go with x squared minus 4x minus 5. But on the bottom, I'm going to put x squared minus 25. Let's go ahead and graph this one so you can see it. X squared minus 4x minus 5 over x squared minus 25. All right, pay attention to this one. This one's an important one. All right, do you see any x-intercepts? Yes? Where does it look like it is? Negative 1, right? Looks like we just have one x-intercept at negative 1. Okay, so it looks like I have an x-intercept at x equals negative 1. How about vertical asymptotes? Do you see any vertical asymptotes there? Does that look like negative 5 to everyone? And negative 5 right there, yeah? X equals negative 5. We have a vertical. Is that the only one you see? Yeah, that's the only one I see. So x equals negative 5. And then we have horizontal asymptote. We can do this one by just looking at this. Like, forget the graph. This is 2, right? They're the same? So 1 and 1, what's 1 divided by 1? 1. So we should expect to see a horizontal asymptote y equals 1, which I think you would agree with me, it looks like y equals 1, right? Yeah? Okay, but watch, there's an issue. If I factor the numerator, it's the same as that one over there, right? What's the factoring of the denominator? That's a difference of squares, right? So x plus 5, x minus 5. What is different here than we had here? You'll see it, there's something important. You have factors that cancel. Do you see that? According to this, right, here we said, oh, we should have two x-intercepts, right, at 5 and negative 1. We should have two vertical asymptotes at 0 and negative 3. But here, we only have one x-intercept, and we only have one vertical asymptote. The reason why is because these factors cancel, right? Those factors cancel. So what is happening at 5? Look at the graph over here. Does it look like there's any issues at 5? Can y'all see it? There's 5 right there. Does it look like our graph has any issues at 5? Does it? No? There is an issue at 5. In the computer, for some reason, it's 2023, for some reason, they don't show it to you. You have to click on it and you have to hover your mouse over 5 and watch what happens when I get to 5. Oh, there it is. What does it say? Undefined. There is a hole in the graph. There is a hole in that graph. How do I know there's a hole? Because, look, remember, I know I said this in class before. When you cancel factors, there's a little asterisk where you're promising me that that factor will never be 0. When I cancel these, I'm promising you x can never be 5. Because in the original function, if I try and plug 5 into this, I'm going to get division by 0. And it's undefined then. So you can never plug 5 into this function. So this canceling, right? This canceling of these factors, this right here, means I have a hole at x equals 5. So that's why when you said about the vertical, he says holes don't look like vertical asymptotes. Okay, so I think we're ready to get into this. What we're going to have to do is have a method where we can graph. If I give you a rational function, you can graph it. We need to pay attention for any holes. We need to look for x-intercepts. We need to look for vertical asymptotes. We need to look for horizontal asymptotes. And then we need to put all that information together and try and sketch it. All right? All right, here we go. And we're going to put the steps. Steps to sketching a rational function. This is going to be pretty long, so I think what I'll do is let me put all the steps up here, and then if you want, you can take a picture of it or something, and then you can refer to it, all right? Or just copy down what I put up here. All right, how to sketch rational functions. Okay, first step, we're going to factor the numerator and the denominator. Now, we may not, that step may not even be required if the original rational function, if the top's already factored and the bottom's factored, then you don't need to do that. But we might need to do that step, factor the numerator and denominator. Now, when you do that, right, step 2 would be to check for what? Holes, right? Check for holes. Because if any of your factors cancel, you have a hole there, right? Right? If any factors cancel, so this happens if any factors cancel, we will have a hole, right? If any factors cancel, we'll have a hole there. All right, the next thing, step 3, is to find the x-intercepts. Find the x-intercepts. How do we do that? We set the numerator equal to 0, right? We set the numerator equal to 0 and solve. Now, keep in mind, when I say numerator, this is after the holes are canceled, right? So you have to cancel out any factors, and then whatever's left, you're going to set that equal to 0. Next step, we're going to find the vertical asymptotes. And how do we do that? Set the denominator equal to 0.